Good morning. This talk will present a slight variation on robust adaptive beamforming that was motivated by an analysis of spectral estimates using random matrix theory. I'll remind you of two classical spectral estimation approaches, one conventional and the other adaptive, and then I'll provide a brief review of robust adaptive beamforming that motivates that we take a closer look at the distributions of two statistics. This leads to an alternative robust adaptive beamforming approach that we'll discuss in more detail. The goal of power spectral estimation is to estimate the power distribution versus frequency for some wide-sense stationary process. And this is usually accomplished by using a filter bank. And this is motivated by what we understand about how wide-sense stationary processes behave as they go through an LTI system. The output spectrum is related to the input spectrum through the magnitude of the frequency response of the filter. Hence, if I were to average the output power of a properly normalized narrowband filter, it should provide a reasonable estimate of the power spectrum at its center frequency. And so historically, two approaches have emerged that differ essentially in how you choose these filter weights. One is conventional and the other is adaptive. This talk will focus on spatial power spectra for sensor arrays. So regarding a conventional approach, if I have a spatial snapshot X of L, which I'm going to assume here is complex Gaussian with zero mean and a covariance R, I can take that spatial snapshot and I can run it through a spatial filter. And then I can average the output power. And this can be expressed in terms of a data sample covariance matrix. And this statistic goes by the name of the Bartlett estimator. And what we're going to do here is we're going to choose the filter weight to be what we call a conventional beamforming filter weight. And this is the form of that conventional beamforming filter weight. If this was a uniform linear array, then this filter weight would look like an FFT filter. And when we say that the filter weight is conventional and the spectral estimate is a conventional spectral estimate, what we mean is that this filter weight is independent of the data. All right, and K here is my wave number vector, R is my sensor position, and theta is my spatial frequency, also equivalent to angle. And so if I were to average the output power and plot this versus frequency, it would yield an estimate of the spatial power spectrum. Now, Capon took a different approach. He said maybe we should consider designing these filters in an optimal way. So he proposed this optimal design for the filter weights and basically said, we should consider choosing W to minimize the output power such that we maintain a unity gain in the direction we're looking in. This minimization of output power can be interpreted as a filter stop band constraint, and this unity gain in the direction that I'm looking in can be interpreted as a pass band criteria. The solution is known as the MBDR filter, and this optimal solution, you should notice, depends on the true data covariance. Hence the name data adaptive approach. The output power associated with this optimal filter is given by this expression, and this motivated Capon to propose the following power spectral estimate, where he just replaced the true covariance matrix with the sample covariance matrix. And notice that my sample covariance matrix is intentionally the unnormalized version. We'll just normalize the spectral estimates if we need to remove any kind of bias. And so if I were to sweep this over theta, I would sweep out a spectral estimate. All right, now robust adaptive beamforming approaches basically recognize that although this MBDR solution is quite elegant, it turns out to be incredibly sensitive to errors, basically errors in our knowledge of the two parameters we need to compute the filter weight, the data covariance and the array response vector V. Data stationarity, and imperfect knowledge of the array locations or calibration errors will introduce phase errors that can cause us problems. So phase errors are something that have been studied in quite a bit of detail, and they're known to manifest essentially as a white noise component. And so diagonal loading is used to basically reduce the sensitivity of the processor to these array phase errors. We basically just add this diagonal loading component to the true data covariance matrix, and we use that instead. So practically, we would add a diagonal loading component to the sample covariance matrix. Now, it turns out that this also improves the convergence rate of the sample covariance matrix when there's a true uncorrelated noise component present, which is almost always the case. And so we're formulating the NVDR criteria using this diagonally loaded covariance matrix. We get this solution where we basically just replace the true covariance matrix with a diagonally loaded sample covariance matrix. And we can then compute the filter output power condition on that diagonally loaded sample covariance matrix, and we get this expression. And notice that it depends on the true data covariance matrix, and I've conditioned on the sample covariance matrix that's diagonally loaded. And so we can use this to sort of motivate two robust spectral estimates. If I were to replace R with R hat of alpha diagonally loaded covariance matrix, I get this first power spectral estimate. But if I were to use just R hat, that is the unloaded diagonally loaded covariance matrix, I get a second robust power spectral estimate. And this was something that was discussed by Bagger and Cox in this Asilomar paper. And we're going to focus on the second power spectral estimate because it actually teaches us something fundamental. Just writing the diagonally loaded covariance matrix here in this expression, just recall that it's the sum of two terms. Notice that if I set alpha equal to 0, that this diagonally loaded covariance matrix just reduces to something proportional to the usual sample covariance matrix. So if I plug it into this expression, I get a cancellation, and it actually reduces to a statistic that's proportional to the capon spectral statistic. All right, but interestingly enough, as I let alpha become arbitrarily large, then this identity matrix dominates the sum. And so what happens is when I plug it back into this expression, this just looks like an identity matrix times V, and the denominator becomes constant, and we end up with a statistic that's proportional to the conventional power spectral estimate. So this is interesting because what it suggests is that as we vary the diagonal loading value, we basically end up with a filter that we can think about as a hybrid between a data adaptive filter and a conventional filter. And so diagonal loading, the value that we pick essentially determines the extent of hybridization. And so this sort of motivates us to ask the question, what is the statistical dependence or coupling between these two statistics? And so, and by the way, when I made this, when I looked at the value as alpha approaches 0, I assumed that L was greater than or equal to N. But if we ask about the statistical dependence between these two spectral statistics, turns out that there are a few things that we already know. A very classical paper published by Capon and Goodman in 1970 actually established the marginal distributions of each of these statistics. Basically showed that they were both proportional to complex chi-squared statistics, central complex chi-squared statistics with the indicated degrees of freedom. The proportionality constants are basically given by psi Capon and psi W respectively, where these are just the statistics that you would get if you evaluated them using the true data covariance matrices. And so this is interesting. It doesn't help us in our quest here because they only provide the marginal distributions and they tell us nothing about what the joint distributions would be if they were based, for example, on the same sample covariance estimate. And we want that to gain some insights into robust adaptive beamforming. And so we actually solved this problem, but before I tell you the solution, I want to walk you through a simple exercise here. Assume that I have two linear filters here that are processing the same data observation. Filter W1, W2, and then I can ask what is the coherence between these filter outputs. This is the expression for that, and I can compute this and show that it's given by the geometric cosine between the two filter weights, W1 and W2, where the geometric cosine is actually weighted by the true data covariance matrix R. And I'm going to define this as C phi squared, and notice that this gives me a number that's always between 0 and 1, a real number between 0 and 1, and we can establish that simply using the Cauchy-Schwarz's inequality. Now, if I let the first filter be proportional to R inverse V, like the NVDR filter, that is a filter that maximizes the output SINR, and I just let the second filter be some arbitrary filter W, like my conventional beamforming filter, then this C phi squared takes on this form here. And notice that this can be written as the ratio of phi capon to phi W. There's my phi W and there's phi capon. And this is interesting because this C phi squared, this geometric cosine, actually gives us what we can think about as a measure of the extent of hybridization between a conventional filter and the adapted filter. And interestingly enough, if I were to compute the SINR loss between a filter that maximizes the output SINR and some other arbitrary filter, which means I get a number that's between 0 and 1, it turns out that this is exactly the same as C phi squared. They're one and the same. And so with that definition, let me show you what the joint distribution is. We generalize the Capon-Goodman result and show that each statistic can essentially be written as a function of the same 4 independent random variables. 3 of them are central complex chi-squared random variables with the indicated degrees of freedom, where k is L minus n plus 2, the number of snapshots minus degrees of freedom plus 2, and C phi squared we've already defined, and Z naught is just a standardized complex normal random variable. Now, the left subscript here on the first complex chi-squared is a non-conventional subscript, which I'm just using to remind myself that I'm referring to exactly the same random variable. So this random variable is exactly that random variable. And it turns out that this first equation is exactly the same expression that Capon and Goodman provided. It's the second equation, or equality and distribution, that provides additional information when these are based on the same sample covariance matrix. And so what you can see is that this C phi squared plays a very central role in terms of the dependence between these two statistics. Obviously, because if C phi squared is actually 0, these statistics are independent. And if it's non-zero, they're actually dependent. And if it's equal to 1, they're strongly dependent. All right, and so those are the parameters of my distribution. And because of this major role played by the coherence, it motivates us to use it as the basis for a robust adaptive filtering design. Let the assumed steering vector be V and let the true steering vector be VT. If that's the case, I can define the error between the true and assumed as this epsilon vector, and the covariance I can define as B. So this becomes the covariance of my array errors. Now I propose that we design our filter weights to basically minimize the response of the filter to array errors subject to 2 constraints. One that constrains the look direction to have unity gain, and the other one that constrains the coherence or the SINR loss of my solution relative to a solution that maximizes the output SINR. All right, and we can solve for this. Here's the actual form of the solution you would get. And this lambda gamma acts effectively like a diagonal loading value, and gamma is what I can specify. So if I want this to be a solution that is always no less than within 3 dB of the optimal solution, I would choose gamma to be 0.5. Now, if you compare this to the solution you would get with the white noise gain constraint, what we've done is we simply just reverse what we minimize versus what we constrain. All right, here we actually constrain the response to array errors, where here we're actually minimizing the response to array errors. Here we actually constrain the SINR loss, where here we actually minimize the SINR loss. So we're just changing the roles, but it turns out to have a very interesting effect. So here I'm showing you that it actually works. It does what we expect. I'm showing you the beam pattern on the left. If I just look at the NVDR solution, this is this red curve. But as I begin to accept more and more SINR loss, notice that these deep nulls for the NVDR begin to retreat towards conventional side lobe levels. Okay, so it does the right thing, what we'd expect. And of course, as I'm willing to accept more and more SINR loss, I basically get more and more gain against array errors. And so where the maximal gain here is 10. And if I sort of look at what the differences are between these two approaches, you'll notice that as I vary the diagonal loading level over both a SINR constraint or a white noise gain constraint, I'm plotting the solution in this 2-dimensional space where I'm plotting normalized white noise gain on the horizontal axis and gain against interference on the vertical axis. And I'm basically sweeping out the same space of weights. The difference is that I prioritize gain against interference. So as I increase the interference level, my beamformer doesn't suffer any loss relative to an optimal beamformer, whereas a white noise gain constraint, because I'm prioritizing gain against array errors, I suffer in terms of SINR loss. Ultimately, what you want to do is you want to prioritize whichever one is the dominant interference. And so So that's what we've done here. Generalize the Capon-Goodman result, introduce an alternative robust adaptive beamforming approach that has a nice practical appeal because I can specify an SINR loss, which I can identify with in practice.